Okay, good morning to one and all. So in the previous class, we have discussed about construction and working principle of the LVDT. Okay, is it audible?
Yes, sir.
Screen is visible. Is the screen visible?
Yes, sir.
Okay, so we have discussed about the LVDT. So can anyone tell me what is the long form of LVDT? LVDT. Already discussed it. So I'm asking the long form of LVDT. That's it.
Linear variable differential transformer.
LVDT. So linear variable L indicates that is linear variable differential transformer. So the output side, it has two windings. Difference between that one, it is going to give that one. It is going to give that one here. Differential transformer we are going to consider. Yesterday we have considered that one winding we have considered here, that is called primary. It has two secondary windings like this we have considered, and this is another secondary winding here. Okay, we have connected like this here. So the differential output we are going to get like this. This is the E out. E out we are going to get here now. E out is nothing but it may be S1 and mine. Just here now, two secondary windings are there. Here at initial condition, we are going to use one, that soft iron piece we are going to use here now. We are going to use here now. We have provided the arm for that one here now. So aluminum arm is provided. We can make the displacement in this form here now. Up to here, we can make the displacement of this moving iron here. This is called primary here. So if it is at center null position, so the flux linkage for this coil and this coil both will be same. So the output will be 0. We have discussed it in the previous class. Suppose instead of this middle, so at equal displacement at null position, that is called 0. Suppose it has shifted up or down or left or right, whatever it may be. So suppose it is came down here now. So the flux linkage of this one will be more. So on that condition, E out is nothing but S1 minus S2 or S2 minus S1. That is based on that which side we are going to consider that one. So the differential output, difference of this EMF induced and this EMF induced, we are going to get that one. So one time we'll get positive, another time we'll get negative, that another time we'll get negative here. But it has some limit, that one. Within that period only we are going to do the movement here now. Up to from this area to this area only we can do the movement here. If it is moving here only, up and down or left or right, that will be in linear range, we are going to call that one. So how the displacement is moving here now, like that the output is, it is going to generate here. Initially at 0 position is there. Suppose we are moving here now, like that here now. See here, little this much I have moved, this much output we have got here now. This much I have moved here now. So I got the output here now. Whatever it may be, left or right, you consider that much output I got here now. Suppose I will move this much, then this much output we are going to got. Suppose in the reverse means negative side we are going to get like this. Yes or no? So up to here, the dotted line is there. This dotted line, whatever it indicates here now, This one is nothing but its linear range is there here. It is a linear range is there here. So before this linear range, whatever it is there, that is called in phase. We are going to call that one, which are in phase. Suppose after this linear range, see here, this one, it is look like a straight line. Can anyone reply? It is like a straight line only. Yes or no? So this line, it is straight line or any some slant like this it is there. It is a straight line only, na?
Yes, sir. Yes, sir.
It is a straight line. Linearly, the output of the differential transformer is varying with the displacement here now. That is called in phase here now. Suppose after the linear range, after this one, suppose I will take the soft iron piece outside of this one, half outside, half inside, I will take that one. And that condition, what will happen? It will go out of phase over there. So the output is not linear here now. Slant bend is there here. There thoda bend hai na? Like this aisa ho gaya. Yes or no? Here also. Thoda aisa ho jayega. So that is called out of phase. We are going to call that one. Based on the operation of LVDT. So during this one, if it is within this displacement period or length, if it is varying, then the linearly the output will be increases with displacement. If it is not above the linear range, then it will go out of phase of that one here now. That is non-linear range. It is going to do that one. This is the characteristics of LVDT we are going to call here. This is the characteristics of LVDT. So similar principle is there for the RVDT. How LVDT is operating for the three positions, that is null position, right position, left position. Same operating principle is there for the RVDT. We are going to call that is rotary variable differential transformer we are going to call. Before that, it has the LVDT has some advantages and some disadvantages are there. So the advantage is it is nothing but first one only, it is highly sensitive here now. Small displacement, 0.1 displacement is there, means that one it will changes its output over there. So only for the input we are giving the supply. So power consumption is low here now. So frictionless construction is nothing but, is there any rotating part here? No rotating part. And it is a ruggedness is there for in the differential transformer we are using here now. So these four are the advantages which are applicable for the LVDT. So advantages are there, means some disadvantages also there. Performance is affected by wave vibrations here now. Continuously the transformer we are going to give the input voltage we are going to give, but the movement we are doing means आपका गाड़ी एग्जांपल देता हूं मैंने, ये गाड़ी आपको सपोज डिस्प्लेसमेंट मींस एनीथिंग यू आर मूविंग मींस वाइब्रेशन विल बी ऑकर्स ओवर देयर. So some vibrations are there which will affected by vibrations, the performance will be reduces over there. And for the movement of that one and continuous giving the power supply, the temperature will be affects for the performance of LVDT. The temperature may increase over there. So based on the performance, it may affect, we are telling that one. So vibration will affect, temperature will affect to its performance here there. So it is used to measured in linear displacement. To measure the linear displacement in the industries, we are going to use this one. So it is useful in, what's that, when force, pressure, weight measurement as a secondary transducer, it is going to operate on that conditions over there. So whatever the displacement is there, it is physical quantity. Yes, the physical quantity is there. That one we are going to convert in the form of output here now. Output is voltage, in the form of voltage or current we are going to measure. So physical quantity to electrical quantity it has satisfied. That is called transducer, we are going to call that. So it completes the LVDT. We'll go further for the RVDT, will go that one. That is called rotary variable differential transformer we are going to call. Any doubts in the LVDT? We have any doubts, we can ask in the LVDT. किसी को कुछ डाउट है कि LVDT में? I am
No.
asking to you people. Okay, no. So there is no much difference between LVDT and RVDT. So that is linear. This is rotary. Other things, all other things are same. L and R, only first letters of these two names are replaced now here. L is nothing but linear. Just a linear means linear displacement. The output is linearly vary with the displacement. Here that is called rotary variable difference is that here. That is called rotation here now. We are going to fix one iron part here now, that it is going to rotate here now. So the full form of RVDT is stands for, that is called here. Because of that the internet disconnection occurred. I don't know how much time we'll get the internet connection. So is it visible?
Yes, sir. Yes, sir.
The recording is start hai ke nahi?
Yes, sir.
Chalo?
Yes.
Okay. So the RVDT stands, its full form stands for rotary variable differential transformer. So whatever the rotation is there, based on that, the rotary variable differential transformer we are going to call. It is an electromechanical type here now. We are giving the electrical supply like a motor, it is going to operate here now. The rotation part based on that. So for that reason, it is an electromechanical type of inductive transducer here now. It is a inductive transducer that converts angular displacement into the corresponding electrical signal here now. Angular displacement, previously it is left, right, or it may be up and down. Like this we have discussed. Yes, ऐसा discussion किया ना अभी. LVDT, it is linear. It may be left, right, or it may be up and down. But now RVDT, we are going to rotate it like this in the, what is that one here now? Angular displacement we are going to consider here now. Suppose if it is here, this one we'll consider as 0 here now. This is 0 here now. 30 degree, 90 degree, 120 degree, 180 degree, like that. How much difference is that we are going to consider here now? Based on the degree angular displacement, the output will changes here now. So left and right here now, 0, 180 degree, and this one we have considered 90 and 270 here now. Yes or no? 230 or what it is? 90 plus 260 degree, na? 360 means 270 here now. Okay, this is 90, this is 180 degree, this is 270 degree. Already we have identified by using the LVDT here now. 0 and see left and right we can measure, we have measured. Up and down we have measured. So 90 and 270 degrees, 0 and 180 degree we have measured. But we have to measure now the middle here now. What is this for angular displacement? 0 se idhar aaye to how much voltage we are going to get. And based on that angular displacement, we are going to get the differential output we are going to get. Here also one primary winding, 2 secondary windings are there here. So that is, it is an electromechanical type inductive transducer that converts angular displacement into the corresponding electrical signal here. Whatever the angular displacement is there, that one it is going to convert into electrical signal here now. As RVDT is an AC controlled device here. It is a AC controlled alternating current we are going to give, AC controlled device. So there is no electronic component inside it here. We are not going to use any electronic components. We are not using in that. supply cable. Just a minute. Attach charger. So it is most widely used inductive sensor due to its high accuracy. Now we are going to use inductive sensors because it has high accuracy level here. Now since the coil of RVDT is designed here. Now this coil is designed to measure an angular position here. Now if it is 30 degrees there or 90 degrees there, 60 degrees there, what is the angular position it is going to measure? So it is also known as angular position sensor also. This RVDT is also known as angular position sensor. We are going to call that one. So this is just basic of the RVDT. Just basics of RVDT. It is an electromechanical type inductive transducer we are going to call, and it is also called as angular position sensor we are going to call, because it is going to design to measure an angular position we are going to measure. For that reason the name came, that is angular position sensor we are going to call this one. It is also called as angular position sensor. Next we will go for, see here, this is the diagram. This is the diagram. Again here, see here, once primary winding is there, two secondary windings are there. This is S1, S2 you have considered here now, S1 and S2. EMF induced in the S1 is ES1, EMF induced in the S2 is nothing but ES2 we are going to call that. ES2 we are going to call that. Suppose if we are going to consider that it is moving in the anti-clockwise direction, on that time, see here, it is like this. We can consider vertical position or a horizontal position, initial condition. Like this it is there. If it is anti-clockwise, it is moving here now. So this edge will be related to more flux linkage will be there from primary to the secondary. On that condition, ES2 is greater than ES1, we can tell that one. If it is moving in the clockwise direction, then on that condition, it is like this. It is which is near, it is away here now. So more the magnetic flux link will be there for the S1 coil. So that is called ES1 by ES2. So three conditions we are going to get here now. So EMF induced in the secondary coil equal to EMF induced in the primary coil. That is called ES1 equal to ES2. ES1 equal to ES2. To one condition, that is called null position we are going to call. Second one, ES1 is greater than ES2. ES1 is greater than ES2 and ES1 is less than ES2. That is ES2. Now three conditions we are going to consider. So why we want three condition means, here the output of this one we are getting from the differential transformer here. The two transformers are there. Difference between these two transformer output we are going to get as the final output here. Now for that reason, that is differential transformer we are going to call that. Rotary variable differential transformer. In the rotating form we are observing here now. So for that reason we are going to use one core here we have connected here. It is a shaft is there. This is the rotating part here now. The core is the rotating part. Inside that, whenever the supply we are going to give, the magnetic field will produces, the force will produces. That force it will start to rotate this core here now. Same like a motor operation we are going to consider here. So this is it has AC supply is given to the primary, and primary is one winding only. Secondary it has two windings here now. So same thing we have written here now. So the design and construction of RVDT is similar to the LVDT here. Whatever the design construction is there, similar to the LVDT. In LVDT, how many primary windings were there? How many primary windings was there? LVDT में प्राइमरी वाइंडिंग कितना था? I'm asking to you only. How many primary winding was there in the LVDT? आवाज आ रहा है क्या? Hello. Hello.
Yes, sir.
Yes, sir.
सुबह सुबह मॉर्निंग लेक्चर है, अभी भी रिप्लाई नहीं कर रहे आप लोग. How many LVDT primary winding was there in the LVDT? LVDT में कितना प्राइमरी वाइंडिंग था?
1,
1. Secondary windings?
2,
2. In the RVDT, how many windings are there? Primary and secondary both are same only. So
Yes, sir.
the design and construction of RVDT and LVDT is same only. Only change is there inside whatever the soft iron piece we were used in the LVDT, that is for the linear displacement we have used. Here we have used on the iron core, we have used which one is a rotating part here. Now based on that, the linear and rotary, the name changed here. So the only difference, the design and construction of RVDT is similar to LVDT. The only difference is the shape of the core in the transformer winding here. Now, whatever the inside the transformer winding, we are keeping the core here. Now, in the LVDT, there is a linear soft iron piece we have used. Here, one rotating magnetic core we have used here now in the RVDT here now. So, LVDT uses the soft iron core to measure the linear displacement, whereas RVDT uses the cam-shaped core, that is rotating core, for measuring the angular displacement. In the LVDT, we can measure the displacement of, that is linear, that is it is nothing but left and right, we can call that one. That is a null position, means if it is center, that is on that condition the output is 0. If it is left, we can say that one the positive. If we can write, that is negative, we can say, or it is positive and it is negative, based on how we are ES1 minus ES2 or ES2 minus ES1, how we are going to calculate here now. So that is left and right horizontal displacement we are going to call, and if it is up and down we are considering, that is called vertical displacement. From the LVDT we can measure horizontal or vertical measurement, we can do displacement, we can do in the form of, that is LVDT. But the RVDT is nothing but angular displacement. It is going to rotate 0 degree, 30 degree, 60 degree, 90 degree, like that it is going to rotate here now. So the rotating core we are going to consider here now, instead of the linear core material, soft iron core material, we are using here cam-shaped or rotating core we are using in the RVDT, which one it is going to give the output in the secondary winding whenever the angular displacement takes place over there. If it is shifted, the rotating core is shifted from 0 degree to 30 degree, 45 degree, 50 degree. On that condition, the flux linkage from the primary to secondary through this rotating core will changes. On that condition, the differential transformer, what it will give, the EMF will induces in the both primary wind, so both secondary winding S1 and another secondary winding S2 here now. So the bigger value minus smaller value we are going to get, that is differential output we are going to get that one here. That is called RVDT function, we are going to tell that. Okay, this is construction I am telling here now. Next, the working principle is, the working principle of RVDT and LVDT both are same here now. Again, working principle is also same. There is no much difference between RVDT and LVDT. So the working principle of RVDT and LVDT both are same here now. But only the difference is, that is rotating in the horizontal axis, vertical axis. This RVDT is going to rotate in the angular displacement we are going to call here. So both are the same, and based on the mutual inductance principle only it is they are going to operate here now. Based on the mutual inductance principle only they are operating. We are giving the supply to the primary, it will mutual inductance, because of mutual inductance, the flux linkage will connect to the primary to the secondary through a iron phase. So on that condition, the EMF will induce in the secondary windings, both the secondary windings, the EMF will induce. The difference output of the secondary winding we are going to get, that is the differential output. So when AC excitation of 5 to 10 volt at frequency 50 to 400 hertz is applied to the primary winding of RVDT, we are providing the AC supply to the primary winding. Then what will happen? Then a magnetic field is produced inside that core here now. Whatever the primary magnetic winding is there, so in that one, so magnetic field will be produced inside the core here now. This magnetic field induces a mutual current in secondary windings here. So it is completely the induction, mutual inductance principles are there here now. So the mutual inductance will, so magnetic field, whatever it will produce, so the flux lines, it is links with the secondary winding. Secondary winding S1 and S2 it is going to link here now. So due to this magnetic field induces, because of the mutual inductance or mutual current in the secondary winding, then due to transformer action, the induced voltages in the secondary windings, the EMF will induces in the secondary winding, that is called S1 and S2 here now. So induced EMF in the S1, that one we are going to call as ES1, and induced EMF in the S2, that is called ES2 we are going to call here now. And the differential output we can consider as ES1 minus ES2 here now. So the net output of the differential transformer is ES1 minus ES2 here. This is general working we are telling here now, we are discussing. There are again 3 steps are there, 3 methods are there, that 3 positions are there. Based on their position, it is going to operate again. LVDT, RVDT is also going to operate. If it is at the middle of that one, so the flux linkage between the both the secondary windings S1 and S2 will be same. On that condition, that is null position we are going to call, because EMF induced in the coil S1 and S2 both will be same. So that is null position, and some positions are there, 3 positions it is going to operate here now. So those are case 1 when the core is at null position, case 2 when core rotates in the clockwise direction, and case 3 when core rotates in the anti-clockwise direction. We are going to call that anti-clockwise direction here. Okay, see here, this one I will read. Then due to transformer action, the induced voltages in secondary windings S1, S2, 2 windings are there, are ES1 and ES2 respectively here. So ES1 is nothing but induced EMF in the secondary winding S1. ES2 is nothing but EMF induced in the secondary winding S2 here. Hence, the net output voltage will be the difference between both the induced secondary voltages here now. So the difference between both the induced secondary voltage, that is called output voltage, that is called E0 equal to ES1 minus ES2 we are going to call here. This is the net output of the differential transformer. So now, according to the position of the core, there are 3 cases that arise. So let's discuss these 3 cases one by one in detail here now. So according to the position, if it is at connecting the flux linkage between the secondary winding S1 and S2 is equal, that is called null position we are going to call. If whatever the middle of the core is there, that one it is going to rotate in the clockwise direction, that is called, what we will call, that is the position, clockwise direction position, and anti-clockwise it is rotating, again the flux linkage between the both the secondary windings will be vary. So for that reason, so the anti-clockwise direction position we can call that one here. Now, one by one we'll discuss. 3 positions are there, one by one we are going to discuss here now. When the core is at null position here now, see this diagram I will take here, it is null position now, it is equally, it is connected here now, it is, some flux linkage is connected to the S1, some flux linkage. It is center of the both the secondary windings. S1 and S2 को center में है भी ये. Yes or no? The core is at center now.
Yes, sir.
So on that condition, the flux linkage between the S1 and S2 will be same only. So when the core is at null position, then the flux linkage with the both the secondary windings will be same. Null position or reference position are middle of the between middle of the secondary winding S1 and S2. So it is equally connecting to the S1 and S2. On that condition, the flux linkage will be equal. So if the flux linkage will be equal for both secondary windings S1 and S2, on that condition, EMF induced in the coil S1 and S2 will be same. So the induced EMF ES1 and ES2 in both the windings will be the same. You know. So the what is the output formula? Net output is E naught equal to ES1 minus ES2. So the output we are using here now, E naught equal to ES1 minus ES2. Here at null position, we are going to get ES1 equal to ES2. On that condition, ES1 minus ES1 or ES2 minus ES2, that is called 0. The net output is 0. We are going to call here now. So that it indicates the output is 0. It indicates what? There is no displacement of the core at all. There is no displacement at all here. No, there is at initial condition only it is there. We can assume that one here. Is it clear? Null position. Yes. So next one, the second case we will discuss about that. That is called case when the core rotates in the clockwise direction. So the clockwise direction is in this format if it is rotating here, if it is rotating. So then this case, the flux linkage with S1 will be more as compared to S2 here. Will be more as compared to S2 they are telling here now. How they are telling here now? Initial condition, see here, I will draw the diagram, then you will understand that. Here the primary winding is there. Okay. Here the S1 I will consider. This is the S1. This is S2. S1, S2. I will draw that the magnetic core is in this position here now. I will call this in this position. I will call that one null position. I will take in the 90 degree first. Initially, it is there at 90 degree here now. Barabar. So equally it is connected here now. This core is either half middle में connect हो गए. So half is connected to here, half is connected to here. You can think that one. This is the null position now. Visible है क्या सबको? The diagram is visible or not?
Yes, sir.
So at null position, this is the null position we are going to call that one. So the primary I am going to give the supply. So because of this supply, because of mutual inductance will be produced this and it is going to connect to the core and core to the S1 and S2 here. Now, if it is null position, half equal part is connected to S1 and S2 here. Now, so on that condition, the EMF induced in the S1 and S2 will be equal. So the net output will be E naught equal to 0 at null position here. E naught equal to 0 at null position. Suppose it is going to connect in clockwise direction they are telling here now. Clockwise direction means which one? Left to right or right to left? Clockwise means like this or like this. First one or second one? This is first, this is second. Clock one means which one?
Second one.
Second one. Okay. So Clockwise means second one you told that one. So this, whatever the pointer is there, this coil, it is going to move like this. I'll take another color here, yellow color I will take. So in the clockwise direction, it is going to move like this. Yes or no? Yellow you consider here. So the core, whatever the middle core is there, which is connected to S1 it is connected nearer to the S1 or nearer to the S2 here?
S1.
S1 it is nearer. So it is nearer to the S1. So on that condition, what will happen? The EMF induced in the S1 will be more and as compared to the S2 here now. As compared to the S2 here now. So what will happen? Our formula is there. So in this condition, we will get ES1 is greater than ES2. ES1 is greater than ES2. What is the formula for the net voltage? Net output of this one will be E0 equal to this one. E0 equal to ES1 minus ES2 here now. So ES1 is positive and ES2 is lesser here now. So the sign of ES1 only we are going to get, bigger value minus smaller value. So the output will be in positive or negative here?
Positive.
Positive output we are going to get, because ES1 is greater than ES2. We can say that one. We can say that one here now. So this one I will consider as E output, the net output here now. See, why I am drawing this diagram is that one they have taken only reference line they have drawn, but here we can understand more. Okay, so it is shifted left. It is means clockwise direction may shift ho gaye, to we are going to get the output as positive. We are going to get here. I will remove all the things. All positions are there here. This is which position it is? थोड़ा confusion हो गए तो मैं बोल देता हूँ 1 मिनट.